At 0530 on the morning of July 16, 1945, the pre-dawn stillness of the New Mexico desert was shattered by the most momentous man-made explosion of all time. This was the fiery birth of the atomic bomb, culmination of centuries of step-by-step advance in the scientific quest, achievement of intense international effort by the Democratic Allies, product of unremitting research and toil since 1939. This instant of fury and flame and of violence beyond conception sounded the end of an age and heralded a new era in the destiny of mankind, a new relationship of man to his universe. Only a few carefully selected technical and military observers witnessed this test of new power that rocked the countryside at Alamogordo. The dramatic experiment took place just 6 days after provision of sufficient material for the first bomb. Development and construction of the bomb was the most closely guarded secret in scientific history. Solemn acknowledgement of success by 2 leading scientists foreshadowed the gravity of events to come. A world steeped in war did not know that a fearsome day was drawing near. On August 6th at 0815 Japanese time, an Army Air Force B-29 dropped atomic bomb number 2 on Hiroshima, Japan's 7th largest city, a communications, military, and industrial center of considerable importance. A stunned universe now swiftly learned that man had a new weapon of shocking destructiveness, a weapon bordering on the absolute. In the blast, thousands died instantly. 70,000 persons were killed or listed as missing. 140,000 persons were injured. Of these, 43,000 were badly hurt. The city was unbelievably crushed. Of its 90,000 buildings, over 60,000 were demolished. The desolate remains were aptly described as vapor and ashes. Man had torn from nature one of her innermost secrets, and with his newfound knowledge had fashioned an instrument of annihilation. Menacing implications of this extraordinary weapon were frightening to everyday people.
Well, what did you think of that bomb we dropped on the Japs, Mrs. Glenn?
Oh, isn't it terrible? All those people killed.
3 days later, another B-29 dropped an improved bomb on the major Japanese seaport of Nagasaki, a highly congested, industrialized city boasting the best natural harbor in western Kyushu and extensive naval facilities. This bomb, exploding over the North Factory District, took the lives of 42,000 persons and injured 40,000 more. It destroyed 39% of all the buildings standing in Nagasaki before the calamity. The Japanese described their bleak, mutilated city as a graveyard with not a tombstone standing. These 2 terrifying blows were struck at Japan only after profound consideration of all the human and military factors involved. The atomic bombs were dropped to end the war quickly, and they did end the war quickly.
For 3 years, gathering momentum with each small victory, our forces had conducted an offensive against the war-bloated empire of the rising sun. Slowly, island by island, mile by mile, and then with ever-quickening sweeps, the combined land, sea, and air forces of the Allies drove against the borders of that empire, forcing it back until late in 1945, only the bastions of the Japanese home islands remained to be stormed. Our submarines were already roaming the Sea of Japan. Planes were devastating cities almost at will. The back of Japan's military might had been broken. Her navy was smashed and useless. Her marine transport was destroyed. Her industrial power was crushed. All this had been accomplished only with great sacrifices of killed and wounded among our personnel and tremendous cost of equipment and supplies. Ahead lay the greatest campaign of all, invasion of the Japanese homeland and close-in, desperate fighting. That this fanatical enemy would not quit until her last fighting man had been driven from his cave and killed had been established time and again by bitter experience. The price to be paid in casualties for successful invasion of Japan could not be estimated in exact dimensions. That the cost would be greater than in any other campaign of our long history could not be denied. This fact was accepted in its stark reality as plans to launch the invasion were completed. Ships in strong armadas, planes in great flotillas, men in vast numbers were already being gathered under a pre-Alamogordo strategy that had not been able to count on the aid of atomic weapons. Secretary of War Stimson, explaining the situation which existed when the atomic bomb became available for use against the enemy, designated employment of the bomb our least abhorrent choice. Weighed in the balance, he said, were the lives of thousands upon thousands of our fighting men. The total of United States military and naval forces engaged as potential combatants was 5 million men, plus millions more of our allies. The Japanese still had intact army forces of 5 million who would seek to repel the invasion. It was vitally necessary then to produce the greatest possible blow upon the Japanese people if the war were effectively to be shortened. Should the war follow a normal course, even with fortune favoring our efforts, military leaders estimated that it would be late in 1946 before the end of the war was in sight. 12 more months of war. The blow must be struck. It must be struck in a way that would leave the enemy no recourse, no choice, but quick surrender. A demonstration bomb on uninhabited Japanese territory was rejected by a responsible panel in that it would prove inconclusive, risk the security of the weapon, and fail to deliver its intended psychological blow. On July 26, 1945, the Japanese were solemnly warned of the penalties of continued resistance by the terms of the Potsdam Declaration, signed by President Truman and by Prime Minister Attlee of the United Kingdom, with the concurrence of Chiang Kai-shek, President of the National Government of China. Thus, the terms Japan later accepted were offered in advance of the atomic bombing. The Japanese rejected the Potsdam Declaration as unworthy of notice and fought on. President Truman made the final decision: the atomic bomb would be used.
At Hiroshima and Nagasaki, the atomic bombs destroyed the cities as entities. In panic, the populations of both cities fled. At Hiroshima, it was 30 hours before the first rescue teams were organized. What the bomb had produced was concentrated chaos, chaos from which no city of any nation could easily or rapidly recover. In these Japanese cities, no significant repair or reconstruction was accomplished until months later. The fabric of community life had been shredded in an instant. The Japanese proclaimed atomic bombs unendurable. 3 days after the second bomb was dropped, on August 12, 1945, the Japanese government surrendered unconditionally. Winston Churchill estimated that the lives of 1 million Americans and 250,000 British soldiers and sailors had been saved by this sudden shortening of the war. Statements of different aspects came from leaders who deplored employment of such a bomb. Solemnly aboard the Missouri, the Japanese signed the surrender documents. Advent of peace was signal for unrestrained rejoicing, but true and permanent peace was still to be accomplished, and atomic energy was a prime factor in the pattern of all negotiations.
What is the atomic bomb? What is this new and terrifying source of power which has intruded itself into the life and thoughts of each citizen? To the average individual, concept of nuclear fission was a remote component outside the orbit of his routine life. He regarded it as beyond the layman's comprehension. The bombing of the Japanese cities thrust it suddenly into his consciousness, made it real, made it a thing that would affect him and you and me and everyone, even in this generation. He did not quite understand it immediately. In the clutter of technical dissertations on the subject, in the press and from lecture platforms, he encountered conflicts and contradictions which confused him. Dire predictions by apparently reputable experts of such things as chain reactions which would disintegrate the Earth in one huge explosion left him with an uneasy feeling that man was tampering with the supernatural, that science had overplayed its hand. Gradually, with a sounder educational program and with time acting as an information filter, the basic elements of scientific progress in atomic research became more clear. With knowledge, panic began to disappear. It was replaced by certainty that man does now have access to new, annihilative or beneficent forces, forces summoning the wisdom and judgment of the ages in forging methods of control and in thwarting any application to evil ends. As a matter of fact, atomic science is not a new science, although the atomic age was thrust quite suddenly upon us, smashing the web of history, violently separating past from present. Yet in the explosion at Alamogordo, no great new principle of nature was either discovered or revealed. Although the atomic bomb was developed in the United States by an international group of allied scientists, impelled by the dread that Germany would develop such a weapon first, and although only one nation at present possesses an atomic bomb, no single nation can claim monopoly of atomic knowledge. Like most major technical developments, atomic science is the product of centuries of provisional conjecture and of experimental probing into the nature and structure of matter. All this started with the ancient philosophers and alchemists. Science began emerging into the light of historic days with Thales, the Ionian Greek, who described the power of attraction in electricity long before electricity as such was known. So-called father of the atom was Democritus, the Greek natural philosopher. Although he had no experimental evidence to support him, Democritus argued that all matter must consist of a number of fundamental pieces. He called these pieces atoms, thus bequeathing the word atom as a misnomer, for atomon, the Greek word, meant indivisible. 79 years before Christ, Lucretius, the Roman poet-philosopher, expounded atomic theory. After the downfall of Rome and throughout the Middle Ages, the atomic view of matter was nearly lost. Aristotelian philosophy, which implied a conflicting view, the continuity of matter, held sway during the long centuries. Then the 17th century brought the age of Galileo, regarded as the father of modern physics. The 18th century produced Isaac Newton with his physical laws. Man's conception of his universe was changing. There followed a procession of scrupulous observers of nature, endlessly asking of themselves and of others why and wherefore. Among them were John Dalton, the English chemist, with his atomic theory. Avogadro, the Italian chemist, who distinguished between the molecule and the atom. Berzelius, the Swedish analytical genius who undertook measurement of atomic weights. Michael Faraday of Irish extraction, the great exponent of experimental science. James Clerk Maxwell, Scottish physicist, stating that atoms were the foundation stones of the universe. Lord Kelvin, practical English genius, who systematized knowledge of mechanics, electricity, and heat in formulation of the laws of energy. Mendeleev, the Russian teacher, discoverer of the periodic system of the elements, who opened new vistas of atomic knowledge. Röntgen, German professor, whose discovery of X-rays provided for science a revolutionary tool. Becquerel, the French experimentalist, who discovered the phenomenon of radioactivity. Max Planck of Germany, who established the law of radiation, which led to the theory of quanta and modern understanding of the electronic structure of matter. Truly the parents of the future science of nuclear physics were the French team of Pierre and Marie Curie. From them came realization that the atom has a core or nucleus, quite different from the shell of the atom. it became apparent that the nucleus is governed by different laws of physics. Concentrating in the atomic field were great laboratories like the Cavendish Laboratory of Experimental Physics at Cambridge, England, fount of so much advanced knowledge in atomic science. Here worked Sir J.J. Thomson, who in 1897 discovered the electron, and his pupil, that giant of atomic exploration, Lord Rutherford, from whom first notions of the proton came, and who discovered and named the proton. He was the first to disintegrate the nucleus. He established the character of radium emissions and suggested what the true nature of the atom might be. Max von Laue of Germany interpreted the crystalline structure of matter, clue to the secrets of atomic structure. In 1905, Albert Einstein wrote the mass energy conversion equation. This was a great milestone, a great victory of man's genius. Einstein unlocked a treasure trove for experimenters. He provisioned them for vast new marches into the unknown. A student and co-worker of Lord Rutherford, Sir James Chadwick, in 1932, discovered the third fundamental particle of the atom, the neutron, an ideal projectile for splitting the nucleus. Final clue to the discovery of the neutron was supplied to Chadwick by Frederick Joliot and his wife, Irene Curie-Joliot, who had observed a peculiar property of the radiation emitted when beryllium is bombarded with alpha particles. Millikan measured the charge of the electron, and Anderson discovered the positive electron and the mesotron. Enrico Fermi, outstanding Italian physicist, in 1934 bombarded uranium with slow neutrons and created new elements. One of the best devices for producing new isotopes and new elements is the cyclotron, developed by Lawrence of the University of California. Niels Bohr, Danish physicist, is chiefly responsible for the planetary conception of the atom. First to probe the atom with X-rays was the young British physicist Moseley, who established atomic numbers of the elements through studies of their X-ray spectra. Deuterium, or heavy hydrogen, was discovered by Harold C. Urey and a group of associates. Rutherford called it one of the most important discoveries of the century. Heisenberg, collaborating with others in Germany and Denmark, elucidated the structure of complex atoms and announced the principle of indeterminacy of physical measurements. 1938 brought the startling discovery of fission of the uranium nucleus by neutron bombardment. Leading names in this research, carried on in Germany, were Dr. Otto Hahn and Dr. Fritz Strassmann. Lisa Meitner, working at Copenhagen, soon demonstrated that fission of the nucleus was accompanied by release of enormous amounts of energy. Allied scientists recognized that uranium fission was of far-reaching and practical importance, not only because of the tremendous release of energy with a single nuclear fission, but because of the possibility of self-sustaining chain reactions. Swiftly, scientists in the United States confirmed the German discovery. This was accomplished in January 1939. At this juncture, Allied interest in the military possibilities of atomic weapons began. Quietly, a military race was started. Free interchange of scientific information came abruptly to a halt. In the fall of 1939, Dr. Einstein wrote his now famous letter to President Roosevelt explaining the urgency of work on uranium fission. Roosevelt, a man of action, moved swiftly. An advisory committee on uranium was appointed. At the Bureau of Standards, the committee first met on October 21st, 1939. 8 recommendations were made to the President. Mentioned as possibilities were atomic power and an atomic bomb.
Time was short. Great Britain and France were already at war. The inevitable entry of the United States was accepted. Fear of German research stimulated activity in the United States and in England. One reason for the decision to concentrate forces against the Germans was recognition that German scientists could produce weapons of great devastation. The scientific competence of this foe was never doubted. Comparable peril from Japanese science did not exist. Early in the war, Allied intelligence had disclosed that Germany was increasing production of heavy water in the famous Norwegian hydroelectric plants at Rjukan and Vemork. These plants also produced vitally needed ammonia. The Nazi war regime was using heavy water for uranium research and also to improve the financial position of the Reich. Just before the invasion of Norway, the French government had purchased virtually the entire world stock of heavy water. At the time of the fall of France in June 1940, Joliot had sent 165 liters of the water to England. This heavy water, which twice had nearly fallen into German hands, permitted vital experiments to be conducted later at the Cavendish Laboratory, research which aided the Allies immeasurably. In the winter of 1942-43, with heavy loss of life, patriotic Norwegian saboteurs and British commandos wrecked equipment in the plants, and the Army Air Force did a neat job of strategic bombing which left the plants crippled. Meanwhile, a ferry carrying heavy water bound for Germany was sunk. German scientists made great strides in nuclear research, just as they had in aerodynamics and in rocket warfare. Their conception of an atomic bomb was an atomic pile guided out of control. They worked hard, but when the war ended, they still had not succeeded in creating a self-sustaining pile. They overlooked the use of a three-dimensional lattice and the role of fast neutrons in achieving detonation. They produced no plutonium. When Strasbourg fell, German atomic documents were recovered and a few physicists captured. Strategic circles then learned that vaunted German progress had lagged behind our own. News of the bomb drop at Hiroshima was a shocking surprise to intern German physicists. They had believed that construction of an atomic engine must precede a workable bomb, and that without German help, no bomb could be built. In June 1940, President Roosevelt organized the National Defense Research Committee. The Uranium Committee became a part of this group, reporting to Dr. Vannevar Bush. As Dean Pegram returned from a survey of British atomic research, Dr. Bush and the National Defense Research Committee determined on an all-out effort to develop an atomic bomb.
Chadwick and the other physicists agree entirely with us that given pure uranium-235, we can make a bomb that will work.
I'm going to see the president tomorrow. I'm sure that he will agree that the job has got to be done and that we'll get the support that we need.
Pearl Harbor had plunged the United States into war. An effective partnership of scientists, engineers, industrialists, and the military was formed. Work in universities and independent research laboratories was coordinated. Manhattan Engineer District, a new branch of the Army's Corps of Engineers, was established to administer work on military uses of uranium. Major General Leslie R. Groves was placed in charge of all activities of the project. The end of 1942 was a critical period. On December 2nd, the first self-sustaining chain-reacting pile was successfully operated at the University of Chicago. On that day, without fanfare, far from the field of battle, the atomic age loomed upon the threshold of history. This success galvanized authorization for construction of the great Clinton diffusion plant at Oak Ridge, Tennessee, and the giant plutonium-producing plant on the Columbia River at Hanford, Washington. Now the task assumed tremendous proportions in expenditure and effort. The expense was staggering, the obstacles gigantic, the possibility of failure ever present. Development of the atomic bomb eventually cost $2 billion. Scaled against the cost of total war, this figure loses magnitude. When the second bomb was dropped, the war had cost the United States $286,748,000,000. The daily cost of continuing the war was roughly $213 million. The plants at Hanford and Oak Ridge took form rapidly. The Oak Ridge pile started operating on November 4th, 1943. The first of 3 piles at Hanford began operation in September 1944. The Oak Ridge plants were designed to concentrate U-235 by different methods. U-235 is one of the 5 known isotopes of uranium. The Hanford plant was the source of that new man-made element, plutonium. Activity progressed at fever pitch. Problems, ugly, difficult, seemingly insuperable problems appeared. By dint of concerted effort, they were solved. As we look back now, what was accomplished appears as day-to-day miracles on a production line. At the time, it was work, 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 and more work. The first atomic bomb was assembled at Los Alamos, a secret laboratory in New Mexico. Scientific equipment was first obtained from universities and research projects. New equipment, built to specification, soon made Los Alamos the best-equipped physics laboratory in the world. When Dr. J.R. Oppenheimer arrived in March 1942 to take charge, he began to surround himself with a galaxy of outstanding scientific stars. The roster included many of the recognized leaders in modern-day physics and technical specialists from all parts of the world not then under enemy control. Sir James Chadwick headed an array of top British physicists at Los Alamos, and this group made invaluable contributions to technique and design. Professor J.D. Cockcroft, first to split the lithium atom in 1932, was another British consultant who gave vast help. Niels Bohr, one of the modern giants in physical science, made himself available after his escape from Denmark via Sweden. From Los Alamos came the bomb design and treatment of many theoretical problems. Measurements of the nuclear constants were refined and extended. Methods for purifying materials to be used were developed. Finally, in July 1945, a practical bomb was completed. This, briefly, is the history of the development of the atomic bomb. It was the harvest of science from many centuries, harnessed to the concentrated efforts of the greatest gathering of scientific brains ever assembled in one group with a single objective. When these men on July 16, 1945, exploded the first bomb in the Trinity test at Alamogordo, they were not releasing upon an unsuspecting world a weapon of unknown potentialities. The power of the bomb had been predicted within close limits by careful calculations, and while the explosion definitely was greater than the average expectation, it did remain within the calculated limits. Military weapons dependent upon nuclear energy were now and henceforth an inescapable reality. Energy released by explosion of one atomic bomb of the type used at Nagasaki is roughly equivalent to that generated by exploding 20,000 tons of TNT. 20,000 tons. 40 million pounds of TNT would fill 2 good-sized cargo ships. Yet, all this energy was contained in one bomb. Nor is this all. In the early stages, the explosion reaches a temperature unmatched except inside the stars. The light radiated from its surface can produce burns well beyond the dangerous range of blast alone. During the burst, there are radiations traveling at tremendous speeds and invisible to the eye that reach even those protected by tile and concrete walls or metal shields. These are gamma rays and neutrons that penetrate and kill with insidious efficiency. Danger persists after the blast has died away. Lethal materials, fission products, and the dregs of the bomb float about over the debris and beyond it. These exist in quantities equivalent in radiation to hundreds of tons of radium. Where they settle is death. These radium-like products give the atomic bomb its greatest deadliness. Under favorable conditions, they may last years or even centuries in dangerous amounts.
The cities of Hiroshima and Nagasaki were selected as targets after exhaustive study by military specialists, blast experts, and weather consultants. An air burst at about 1,800 feet was decided upon to minimize the lingering effects of radiation by dissipation of the bomb products in the atmosphere and to achieve maximum blast effect. Comprehensive studies by Japanese and by Allied scientists were made at the end of the war in both ruined cities. Damage from blast and from primary fires generated by the heat was unparalleled. Buildings collapsed, electrical systems were shorted, stoves overturned. A wave of secondary fires resulted, adding to the Holocaust. Flash burns from primary heat waves caused most of the casualties to inhabitants. Others were burned when their homes burst ablaze. Blast pressure and flying debris caused many injuries. Highly penetrating radiation from the nuclear explosion had a heavy casualty effect. A firestorm with winds of from 30 to 40 knots followed the blast at Hiroshima as air was drawn to the center of the burning area. Sheltering hills caused Nagasaki to be spared the secondary effect of a firestorm, although severe fires resulted from the blast. At first glance, damage at Hiroshima seemed more spectacular than that at Nagasaki, but comprehensive investigation told a different tale. Trees toppled at Hiroshima were uprooted. At Nagasaki, trees were violently snapped off at their bases. The radius of severe damage at Nagasaki was greater than at Hiroshima. Gamma radiation and neutrons caused thousands of cases of radiation sickness in Japan. First, the blood was affected, and then were impaired the blood-making organs, the bone marrow, the spleen, and the lymph nodes. Irradiation killed the young and immature lymphocytes. Germinal centers disappeared. The lymph glands decreased in size, leaving only walls and partitions. Blood would not coagulate and oozed through unbroken skin or seeped into many of the interior body cavities. Next, internal organs such as lungs, intestines, the liver or the kidneys were affected and their functions destroyed. When the irradiation was severe, organs became necrotic within a few days, marking the victim for certain death within a short interval. When the irradiation was moderate, many persons lingered from 2 to 6 weeks before the onset of death. Slight irradiation, when it did not cause death, often produced internal effects which lingered for months. Many persons who escaped both blast injury and burns were cut down from seemingly blooming health by the insidious radiation. Frequent symptoms of radiation sickness were exhaustion, then bleeding or high fever. As gamma rays took effect, rescuer often died before the person he had rescued. Surveys disclosed that severe radiation injury occurred to all exposed persons within a radius of 1 kilometer. Serious to moderate radiation injury occurred between 1 and 2 kilometers. Persons within 2 and 4 kilometers suffered slight radiation effects. When the war with Japan ended, a great mass of information about the atomic bomb had been gathered. But after the explosions at Alamogordo, Hiroshima, and Nagasaki, much scientific information was still incomplete. Lacking was significant information about blast efficiency, nuclear radiation, spectra, time developments, and thermal, magnetic, oceanographic, meteorological, seismic, and biological effects. There had been scant opportunity to obtain by careful measurement the multiple data required for complete statistics. Unavoidable lack of special instruments, lack of time, and loss of some instruments due to unpredictable factors had diminished results at Alamogordo. At Hiroshima and Nagasaki, too few measurements of radiation or pressure were made, and data on injury to personnel, while extensive, were far from complete. Physicians often did not know what type of injuries they were treating. The injured received little or no medical treatment, and trivial injuries often became serious. Methods of treatment were inadequately developed. Correlation of damage and injury data with pressure and radiation data was a subject on which more accurate information was essential. Physical effects of atomic explosion near or under water were entirely unknown. Information on all characteristics of atomic explosion was essential and could be obtained only under carefully controlled conditions. Medical reports needed amplification, especially with respect to the effects of radiation on personnel under varied conditions and the extent of radiation from bombs exploded under different circumstances. New bombing techniques had to be developed and new bombing tables worked out to meet the exacting requirements of this new weapon. The effects of atomic bombs on all types of military equipment demanded study. Beyond question, post-war research, design, and expenditures for national defense would be gravely affected. Only 2 atomic bombs had been used against the enemy. Both were aerial bursts in which the bomb was detonated above land targets. The effects of atomic bombs on ships in both aerial and underwater explosions must be explored to elicit and evaluate fundamental information. Application of information obtained to naval design, tactics, and strategy was essential to national security. Sea power has played a vital role in our destiny as a nation. It was important to know if and how the basic concepts of sea power were to be affected by weapons radically new. All this information was paramount in planning experimental work, in developing the effectiveness of the bomb, and in seeking to discover measures of defense. We could afford to be ignorant of no aspect of the bomb. In the light of this unsatisfactory situation, proposals were made to conduct controlled tests with atomic bombs to obtain all possible information. A program of large-scale controlled tests of other modern weapons had already been projected. The use of the atomic bomb as the implement to produce graded structural damage was expedient because it permitted the combination of damage analysis with studies of atomic effects. Individual proposals to conduct atomic bomb tests had come from General Arnold, commanding general of the Army Air Forces, and from Vice Admiral E.L. Cochran, Chief of the Bureau of Ships, and Vice Admiral G.F. Hussey, Jr., Chief of the Bureau of Ordnance. Leading legislators and Manhattan Engineer District agreed that full-scale tests must be undertaken. As early as 1944, it had been planned to use the atomic bomb against the Japanese fleet at Truk. But by the time the bomb had been developed, the base at Truk was no longer strategically important in the Pacific War. After the war, many proposals to use Japanese vessels as targets for atomic tests were advanced. Such proposals aimed at obtaining required information and at the same time eliminating Japanese naval power completely. It was soon obvious that tests against enemy vessels alone would not develop sufficient information. Basic differences in ship design and tactical policy between the United States and other navies rendered the use of some American vessels imperative. Because our attitude has been traditionally defensive rather than offensive, we needed to discover how United States ships would fare under atomic attack. We needed to re-examine the principle that ship design be matched to tactical function and similar tenets of naval doctrine. The shortcomings of comparative tests with miniature models and conventional explosives were equally obvious. Basic data must be derived from effects of the bomb on existing designs and structure. With such information at hand, model tests could then be continued and experimental work intelligently prosecuted. It was first necessary to formulate the so-called damage law for this new explosive with respect to ship targets and their orientation to blast.
On October 16, 1945, Fleet Admiral Ernest J. King proposed that the atomic tests be controlled by the Joint Chiefs of Staff. A committee headed by Major General LeMay of the Army Air Forces was directed to make studies and recommendations. Result of these staff studies was creation of Joint Task Force 1. With the approval of President Truman, Vice Admiral William H.P. Blandy, Deputy Chief of Naval Operations for Special Weapons, was designated commander of the task force. The Joint Chiefs of Staff approved the code name suggested by Admiral Blandy, and the venture was christened Operation Crossroads. Admiral Blandy was directed to organize a joint staff with adequate representation of the land, naval, and air forces, and with an integrated representation of civilian scientists. Major General William E. Kepner, one of the Army Air Force's top generals, became the Deputy Task Force Commander for Aviation. Rear Admiral William S. Parsons, who had been Associate Director of the Los Alamos Laboratory when the first atomic bombs were made, was named Deputy Task Force Commander for Technical Direction. He was the Enola Gay's weaponeer on the historic flight of that B-29 to Hiroshima. Rear Admiral T.A. Sahlberg, Director of Research and Standards in the Bureau of Ships and Deputy Member of the Tolman Committee for Applications of Nuclear Energy, became Director of Ship Material. Major General McAuliffe, who scorned demands of superior German forces for surrender of his embattled 101st Airborne Division at Bastogne, was appointed Ground Forces Advisor. Dr. Ralph A. Sawyer, now Dean of the Graduate School of the University of Michigan and veteran in the field of applied physics, became the top civilian scientist on the staff. Around this corps of men, Joint Task Force One was built. The Joint Task Force was charged with determining the effects of atomic explosives against naval vessels and equipment in order that strategic implications might be appraised. The directive further ordered that full advantage be taken of the opportunities to gain information on effects of atomic explosions on aircraft and on Army ground equipment, and that all possible data of scientific value be compiled. Secretary Forrestal authorized retention of 158 surplus United States naval vessels for the experiment. Meanwhile, Fleet Admiral Nimitz had saved important Japanese warships from routine destruction, and a choice of these vessels was offered the task force. The Prinz Eugen, modern German cruiser, was earmarked for the tests. The task force commander was directed to procure administrative and logistic support directly from the War and Navy departments, and on matters concerning the bombs to deal directly with Manhattan Engineer District. Assembly of the task force called for coordinated activity by many agencies of the government, notably the Army, Navy, Coast Guard, Marine Corps, State Department, Department of Interior, United States Public Health Service, Smithsonian Institution, Department of Commerce, and the Department of Agriculture. Personnel problems were critical. Highly skilled technicians were particularly hard to obtain. In spite of these facts, Joint Task Force One mushroomed into a highly integrated force of 42,000, with a staff that included more than 550 scientists and engineers. The experiments outlined were to comprise the greatest field tests ever undertaken. Because conduct of the tests would be governed by seasonal weather conditions in the South Pacific, a race against time began. The intricate operation was laid out in minute detail by the operations officer for Joint Task Force One. A planning board met daily to integrate proposals from units scattered over the United States and the Pacific Theater. Even while the master plan was being prepared, preliminary activity was underway at 100 points on the globe, blending coordinated field groups into one great unit. One of the first problems was choice of a site for the tests. The basic requirement called for a protected anchorage 6 miles in diameter in an unpopulated region of the world, but less than 1,000 miles from a B-29 base. The site had to be free from violent storms, must have predictable winds directionally uniform, and predictable currents of great lateral and vertical dispersion. It must have a temperate climate. The site should be remote from fishing grounds, steamer lanes, and inhabited shores, and must be controlled by the United States. After much consideration, a little-known spot in the Marshall Islands was selected. Bikini Atoll, a dot on the map of the mid-Pacific, was destined to become a focal point for the eyes of the world. Situated 11 degrees, 31 minutes north, 165 degrees, 34 minutes east, Bikini met all requirements, except that its population of 167 persons had to be evacuated, and that its lagoon was inadequately charted. Commodore Wyatt visited the island and asked the natives to assist in preserving world peace by allowing their island to be used in the experiments. Even though this meant leaving their ancestral home, perhaps forever, the natives of Bikini were willing to do their share. Family heads selected Rongerik, an atoll 128 miles to the east, as first choice for a place of resettlement. Construction battalion units, with the help of 22 Bikini natives, began work at Rongerik. There were problems of delicate diplomacy in providing just the right number of new houses, just the right number of coconut trees, just the right number of water cisterns. These problems were soon amicably settled, and on March 7th, 1946, King Judah and his people were moved from Bikini and resettled at Rongerik. But the hearts of King Judah and his people are still at Bikini. They live in hope that one day they may return. Bikini Atoll consists of 26 individual islands spread out like beads in a necklace. When the task force was created, the only hydrographic charts available were of Japanese origin. These were inadequate. A new survey of the lagoon was ordered. The USS Bowditch and the USS Sumner, with several other vessels, undertook this survey. Standard sounding methods and the new acoustic bottom scanner were used. Wire drags located horses' heads, obstructions projecting from the coral bottom. While charting continued, troublesome coral heads were blasted from channel areas and potential anchorages. Others were removed to permit submerging of target submarines to desired depths. 40 Japanese mines were located and removed. Navigational markers, buoys, and beacons were placed to simplify movement in and out of the lagoon. The Fish and Wildlife Service of the Department of the Interior endorsed the site for the tests. Fish experts predicted no appreciable damage to fishery resources as a result of the explosions. Extensive tests were initiated to determine the effects of the bursts on marine life. A fish census, before and after, was made at Bikini to be compared with a control census taken at Rongerik. More than 20,000 fish were taken by hook, net, and seine for comparative study and analysis. Establishment of a system of supply was a major issue during these early days of the operation. To cope with this problem, Brigadier General David H. Blakelock, veteran of amphibious supply projects in the Pacific, was designated Assistant Chief of Staff for Logistics. General Blakelock was responsible for transporting, equipping, and feeding 42,000 men, and for installation of all ground facilities. Logistics for Crossroads was a tremendous task involving trains, airplanes, ships, records, fuel, construction and repair facilities, medical care, and the 1,001 jobs of servicing. Presidential delay of the tests added further complication, but eventually was contrived to afford better instrumentation. Aircraft were to play a key role in the tests. As the adaptability of aircraft for technical observation became clear, the relatively simple air plan originally proposed for the tests was expanded. The final concept of air participation utilized 150 airplanes with units from Army and Navy Air Forces. The primary air mission for Crossroads was twofold. First, to put one bomb over the target and to drop blast gauge and other recording instruments in the target area at the right time. Second, to record the effects of both blasts by instrumentation and aerial photography. An air operations plan which permitted flexibility and perfect synchronization was formulated. The lessons learned from projected practice missions were many. Compromises were made between tactical and scientific considerations. Training of air crews was initiated. At Roswell Army Airfield, New Mexico, an ideal location for practice bombing, a spirited competition began among specially trained B-29 crews for the privilege of dropping the Able Day bomb. This competition continued until shortly before Able Day. The desired bombing accuracy was within 500 feet of the bullseye, an accuracy 4 times better than required in normal combat action during World War II. Numerous devices were used to obtain great precision. These included simulated atomic bombs of correct weight, shape, and size. Among the early results were improved bombing tables and improved calculations for wind components. Photographic and instrumentation equipment was installed and tested. At Clovis, New Mexico, the Army Air Forces began tests to determine the modifications necessary to accomplish remote-controlled landings of B-17 drones, break to a full stop, a maneuver never before attempted. After an interval of training, radio-controlled takeoffs and landings of 4-engine planes were accomplished as seemingly routine procedure. Drones were flown above 25,000 feet to test the reliability of control equipment and of televising and telemetering equipment. New high-altitude electrical brushes were designed to improve television. Meanwhile, from carriers off the California coast and from air stations at Atlantic City, Brooklyn, and San Pedro, the Navy conducted training and experimentation with drone aircraft, particularly with catapult takeoffs of carrier-launched drones. During an air rehearsal on May 3rd, 1946, the first launching of a pilotless F-6F was accomplished from the deck of the Shangri-La. Control of the airplane during takeoff was exercised by a pilot sitting in a chair on the carrier deck. Extensive tests with Army B-17 drones and Navy F-6F drones developed standard operating procedures. New and advanced control techniques evolved. At the same time, 6 TBM pilots were trained for air control of 6 drone LCVPs, which were scheduled to recover water samples after each of the explosions for radiological study. Bomb-dropping rehearsals were held at the Albuquerque bombing range, and a full-scale dress rehearsal called Operation Zebra was carried out 100 miles at sea southwest of San Diego. During this operation, a simulated atomic bomb was dropped.
Between March 1st and June 5th, the air units of the task force began moving overseas for continued training. Each unit carried full complements of personnel and equipment. On Kwajalein, a small crescent-shaped island which boasted one of the finest bomber strips in the Pacific, was based Task Group 1.5, the Army Air Forces unit which operated the bombing aircraft. The group was under command of Brigadier General Roger M. Ramey of the 58th Bombardment Wing. At Eniwetok, the Army drone unit was separately based, and here intensive training in radio-controlled flights continued. Sea units, including the carrier Shangri-La, began extensive training operations in the Bikini area with drone landings at Ibai and Roy. A helicopter unit operated from the Sidor and Shangri-La and saw much service during the operations, particularly in the rescue of instruments from contaminated areas. Helicopters can hover, but without pontoons, they cannot float. This rotor plane was dunked on a practice mission. Salvage workers brought her up from the lagoon bottom to permit technicians to study the malfunction. The air movement between the United States and the Marshall Islands was tremendous. Day and night, planes flew the overseas air lanes. Their cargoes ranged from mice to men, from meat to mail. Alone, mail accounted for an average of 40,000 pounds a month. In all, 11,385 passengers and 3,280,000 pounds of freight were transported by air during the overseas period of Operation Crossroads. During the preliminary training period, the major part of the Joint Task Force personnel and equipment, including heavy shore installations, was being moved across the sea in ships. Among the data urgently desired from the atomic bomb tests was the reaction of Army equipment to such explosions, so that designs for new equipment would incorporate maximum resistance and so that new tactical doctrines and measures of passive defense might evolve. Sample equipment was gathered from the Signal Corps, Quartermaster Corps, Engineer Corps, Ordnance Department, Air Force, and Chemical Warfare Service. Coordinating these groups was the Director of Ship Material. Loading the principal equipment was mainly accomplished at West Coast ports. Careful deck layouts were made for exposure of the equipment, which was thoroughly lashed for the voyage and for the violence of atomic blast. Teams of specialists in damage assessment were organized under the Director of Ship Material to observe, record, and assess damage and to relate it to other types of damage after the tests. Test racks of Army and Navy materials were set up on target ships with weathering controls on non-target ships. The major objective of the entire experiment was analysis of the effects of atomic explosion on ships. Preparations to observe and record phenomena affecting ship structures and material were extensive and detailed. Perfection of methods and equipment for this purpose was an enormous task requiring skill, patience, imagination, and resourcefulness. Naval shipyards bustled with activity reminiscent of wartime. Alterations had to be made, new installations had to be completed, time schedules had to be met. Experts on boilers, turbines, pumps, Cranes, ship fittings, electrical equipment, paints, chemicals, lubricants, and fuels had a bewildering assortment of tasks to perform. First concern of the groups, controlled by the director of ship material, was the flotilla of almost 90 target ships, plus reserve target ships. All had to be placed in proper material condition. From these vessels, items of historical importance had to be removed, and equipment which was extremely valuable or scarce had to be salvaged. Wiring circuits had to be set up and diesel generators installed to provide controls and power for equipment which was to be kept operating after the target ships were abandoned. Additional wiring circuits were required for delicate recording instruments. Mounting brackets had to be installed for hundreds of instruments, from pendulums to orientometers. Assembly of data was required on the structural strength and the watertight integrity of each target ship. Serious defects resulting from war damage on some of these ships were corrected. Loading plans were drawn up and followed in precise detail. New anchoring devices were designed. Since the effect of possible high waves on anchored ships was not known, it was planned to anchor each ship with a full scope of chain on one anchor and a short scope on a second anchor. To provide an added safety factor against failure of the first anchor chain, the second chain was hung in loops with fittings designed to fracture, paying out additional chain until the surge had diminished. These fittings were manufactured at Boston Naval Shipyard. Tests were conducted at Pearl Harbor to perfect the anchoring arrangements. 14 of the target destroyers had only one hawse pipe. Portable davits were fabricated and installed to accommodate the second anchor. 130 non-target ships had to be prepared for the many tasks assigned. Aboard some, electrical circuits for instruments were installed and tested. Other ships had to be converted to laboratories. Problems were encountered with the LSM-60 and with the bathysphere in which the Baker Day bomb was to be lowered. This pressure-proof bathysphere was built at Portsmouth Naval Shipyard, where submarines are usually built. The ship was equipped with a sturdy radio mast for multiple antennas. The Cumberland Sound was transformed into a laboratory control ship with elaborate radio equipment designed to arm and detonate the Baker Day bomb. The Albemarle was converted into the bomb-carrying and assembly vessel. The Burleson, headquarters for animal research, had to be transformed into a floating barnyard with feed pens, autopsy rooms, medical storage spaces, and laboratories. The hospital ship Haven was converted to house the radiological safety section. Instrument repair shops and laboratories were installed. 2 rafts of bridging were assembled on the beach at Bikini and towed to the target array for exposure to the explosions. Material was prepared for exposure in landing craft under conditions simulating an amphibious landing. Included was heavy ordnance material in storage condition. There was little rest for workers assigned to reconversion tasks. On target ships, work continued en route to Bikini and up to the final minutes before evacuation of the lagoon for the tests.